Greetings of the day. Welcome back to our channel. If you're watching first time, please like, share, and subscribe to Thisainna Education. So guys, today we're going to start a new chapter. The chapter is Stress and Strain Transformation. In this chapter, we learn more or detail of chapter 1. Chapter 1 basically is the information that we learn in a basic calculation. So this chapter, we're going to learn about further how to be a stress analyzing process. In a plane stress or uniaxial stress, there's a normal stress, which I mentioned earlier in chapter 1. We have the compression stress and the tensile stress. This compression stress and tensile stress are very much important in this particular chapter. Shear strengths are the convention in an application to the plane stress equation. So we need to identify the positive and the negative direction. The shear stress will state in the positive, the direction is to the right and to the up, which is similarly, I always name it to my students 1, 2, 3, 4. 1, 2, 3, 4. So the positive signs are always at 2 and 3. And the negative shear stress is always at 1 and 4. How we can identify this a positive direction or negative direction? As basically, we are getting this information by coordinates. We are following the x coordinate for the accurate value, or we can identify the positive or the negative. Stress on oblique plane under uniaxial load. What I've learned so far, the basic is the axial forces in the two force member cause normal stress, which is the normal stress, one to the left and one to the right, which cause the forces of the equilibrium should be balanced. Same goes to transverse forces exerted on the bolts and pin, causing the shearing stresses. These are the bolts and the pin. As usual, one to the right and one to the left cause the balancing in the equilibrium. Stress on the oblique plane under uniaxial load. However, axial forces cause both normal and shears in the stresses on plane which are not perpendicular to the axis. This is also called a case for the transverse forces exerted on the bolt or pin. Consider the inclined section of the uniaxial bar as shown in the figure. As you see here, where the always sees is not perpendicular to the axis, it can be 45 degree or more. If we identify the first figure, where we can actually show the full load is balanced both sides, and it shows the plane where it is not perpendicularly, and its can be 45 degree, 35, depends on how inclined it was. And based on it, we're going to calculate the force, the new load, and the angle. Stress on an oblique plane under a uniaxial load. The resultant force in the axial direction must be equal P to satisfy the equilibrium, as I told before. The force can be resolved into components perpendicular to the section F and parallel to the section V, where F is the P cos theta and V is the P sin theta. The area for the section is A cos theta, which equals to A over the cos theta. Stress on an oblique plane under uniaxial load. We can formulate the average normal stress on the section S. Shear stress is also force over area, where by using these sections, we can identify that P cos theta over A naught over cos theta equals to P over A naught cos theta cos squared theta. The average shear stress on the section is tau is V over A naught or A theta, which equals to n of the same, which is P over A naught sin theta cos theta. Thus, the normal force applied to a bar inclined section produces a combination of the shear and the normal stress. The main purpose of this chapter, we need to analyze the stress. To stress analyze is using two methods, which is one is the equation method, another one is the Moore diagram method. Basically, these both methods are very important and you need to get the same answer in this both method, end of this both method. In today's lesson or today's video, we're going to show you how to use the equation method. Before we go to the equation, let's study about this equation first. To find the principal stress upon the principal planes at the angles of theta and tau is 0, the formula are shear max or shear mean, shear x plus shear y over 2 plus and minus square root of bracket shear x minus shear y over 2 power of 2 plus the plus the tau power of 2. We have all the formula here. If you want to get easier, you can pause this video and snap all this formula. And we also have the formula for maximum shear stress. The maximum stress always occur in a coordinate system, orientation that rotated at 45 from the principal coordinate system. We also have the normal stress on the y prime and x prime axis. Shear stress corresponding to the x prime and y prime. Example 8. By seeing this example, I'm aware that students can understand much more better. For the state of the plane stress as shown, determine the principal stress, principal planes, maximum shear stress. Okay, first we need to identify the positive and the negatives. We have three sub-questions, which is find the principal stress, principal planes, maximum shear stress. Let's go one by one. By identifying the figure, we can let you know the shear X is 50 megapascal and the shear Y is a negative 10 megapascal. It's going upwards, it shows negative. How about the tau? The tau is 40 megapascal. As I told before, 1, 2, 3, 4. It plays at 2 and 3, which shows it is in a positive. To find a principal stress, we need to find the shear max and the shear mean. By using the formula, we substitute all the information we get. We have a result of plus and minus. At the end, shear max is in a positive, we get a 70 megapascal. Shear minimum is the negative, we'll get the negative 30 megapascal. To find the principal planes, the formulas are tangent 2 theta p equals to 2 tau xy over shear x minus shear y. By using the same numbers or same values, we substitute again and we got the theta 2 theta p because we get 53.1 degree. And 1 theta p, we get 26.6 theta. At last, the C question is finding the maximum shearing stress. Tau max, the formula are square root of a bracket shear x minus shear y over 2 bracket of power 2 plus tau power of 2. We get the answer of 50 megapascal. We also can use the other way, which is the same formula in a different method. Theta S is equals to theta P minus 45. We get the negative 18.4. So here they shown very clearly how it's exactly look like. As I told before, there is our shear minimum 30 megapascal. There is a shear max 70 megapascal. There is the angle of theta P 26.6 degree. As you see here very clearly, we can find the tau maximum and we can find the average of the shear x and average of shear y, and we can see the movement of, or the direction of the movement of the angle is 18.4 degree. Example 9. The state of the plane stress at the failure point on the shaft is shown in the figure. Represent the stress state in the terms of principal stress. Okay, the 90, 60, 20. Good. So as first, we need to identify the established sign convention, that is shear X is negative 20 megapascal, shear Y is 90 megapascal, and tau X and Y is 60 megapascal. The orientation of the element by using the formula tan to theta OP is equals to 2 tau xy bracket over bracket shear x minus shear y. You'll get the answer of the negative 47.49 degree, which the tau p itself is negative 23.7 degree. Recalling that theta must be measured the positive counterclockwise from the x-axis to the outward normal x-axis on the face of the element. Principal stress. First, we need to find, as usual, by using the formula, we find the shear max and shear mean. By using the formula, we substitute the values. We also get the shear max is 116 megapascal and shear minimum is negative 46.4 megapascal. The principal plane on which each normal stress acts will determine the theta negative 23.7 degree, where we need to find the shear x prime. We need to find the shear x prime since the rotation is going to move and is going to get a new value of shear x. So after substituting into the formulas, we get negative 46.4 megapascal. Next example. The state of plane stress at the point of the body is represented on the element as shown in figure. Represent this stress state in terms of maximum in plane shear stress and associate average normal stress. So I think the same value we oriented this now. We oriented the element, we get the theta is 21.3. Maximum in the plane shear stress, we get tau maximum is plus minus 81.4 megapascal. The shear stress correspondingly to the theta 21.3 can be determined by tau negative bracket shear stress minus shear y over 2 bracket sine 2 theta plus tau cos 2 theta. By using this formula, we get the value of 81.4 megapascal. This positive result indicate that tau max is equals to the tau x y prime, x in the positive y prime direction on its face. Average normal stress is always calculated by the shear x plus shear y over 2 divided by 2, where we got the average is 35 megapascal. This is the best and easiest way of the solution by using the equation method. I'm aware some students didn't capture the equation method. This equation can be easy. Listen carefully. All the equations need to follow by order. Then you get the answers. In some situation, there's like this now, we see a situation like some situation we need the x prime values or x or y prime values. In some situation, we need to identify the negative and positive of the angles of the rotations. By this, I'm sure you can handle this formula